So, hello everyone, and thank you for joining this evening lecture of Young Ahmed. I see that there are a couple of more people that have just joined us, so I have to repeat that there is no fire drill planned for tonight. And if you hear the alarm, you will need to evacuate this room using one of the two doors, either the one at the front or the one at the back. So, we have invited tonight Dr. Ahmed Elkady from the University of Southampton to give us insights from recent experimental and numerical research on steel frame buildings. Dr. Elkady earned both his MSc and PhD from McGill University in Canada. He then joined EPFL in Switzerland as a postdoctoral researcher in the Resilient Steel Structures Laboratory. Currently, he is a lecturer in structural engineering at the University of Southampton's National Infrastructure Lab in the UK, and he specializes in steel and composite steel concrete structures, performance-based earthquake engineering, and performance evaluation of structural components and systems through large-scale testing and advanced numerical modeling. Now, that's what his short bio says, which is definitely very factual, but also a bit toned down, probably reflecting the humble nature of our speaker. But I think we can all agree that Ahmed is a brilliant young researcher with some very impactful research in his career and fully justifies the good reputation he has in the UK and abroad. So without further delay, I will hand over to him for tonight's lecture.
Thank you very much. Thank you. All right. Well, thank you very much, Tina, for the introduction. And good evening, everyone attending here in person and those joining us online. Before I start, let me first thank SECED and ICE for inviting me today to give this talk, and also to thank the SECED committee for the huge effort that they do to engage academia and the industry by organizing these regular activities and talks on a regular basis. This is really commendable, so thank you again for that. All right, so today my plan is not to bore you for 40 minutes. So my talk, I will try to keep it as light as possible. So no fancy equations, nothing complicated. So hopefully, even if you are not familiar with the topic, you will get an idea and a sense of this research. Again, as the title indicates, I will just focus on key findings and main ideas and tools that we developed as part of this research on steel moment-resisting frame buildings. And in all the slides that I'm going to show you, I will keep the reference in the bottom right of each slide. So if you would like to read more details about what's in the slide, you can check these publications. So again, this is research that has been conducted within the past 7 to 8 years. So this has been conducted at different universities, funded by different agencies, and definitely contributed by several academics and graduate students that are now all have their PhD. So those I would like to acknowledge first before I go further. And my contribution here is just a part of what the ones that you see here in this slide have done. So I will start by giving just a context to what I'm presenting. And I will start by discussing the performance-based design and loss assessment framework. And this framework, which is becoming increasingly popular, and soon it will become the norm in how we assess and design different structures. This framework pretty much, ignoring this fancy integral that you see on the screen, it integrates different aspects or data, such as the hazard, and the structural response and the amount of damage due to a given hazard and the associated consequences of this damage, may it be monetary losses or injuries or casualties and so on. And this framework, perhaps the most important part of this data is the part related to structural response and the prediction of damage, which I'm talking or focusing about today. And these ones contribute the most to the uncertainty when we assess a structure or structures or design structures. So I'm going to discuss, in order to improve these two aspects, we need to have a good understanding of the damage progressions and the different failure modes in the different structure components. And we need to develop some models and some tools to enable us to do accurate structural response simulations and to be able to predict damage with certainty. In the same time, these models and tools are important because nowadays there is a push for more efficient designs in order to reduce construction cost and to reduce carbon emissions, given the ongoing energy crisis and the climate change that you hear about in the news. So within this framework, we focused on buildings that have steel moment frames, and these buildings are common in construction. And we are focusing within this kind of buildings on four structure components: the moment frame columns, the column web panel zone, and the composite rigid connections, and finally the semi-rigid connections or gravity connections. So I'm going to discuss what we have found or developed with respect to these four components. So I will start perhaps with the most important element, which is the steel frame columns. And this is all discussed within the context, again, of earthquake engineering. So if we are looking at steel moment frames, these are designed to dissipate the earthquake energy by the plastifications of the beam ends. But you still get a plastic hinge formation at the base of the first story column where you have a fixed base. And under strong seismic events, you can get an additional plastic hinge at a higher story, and then you develop what we call a collapse mechanism, which of course we try to avoid in design. Now the question here is, okay, the one that you see here on the screen, this is an example from a shake table utilizing hollow square sections. But the question that we had, how would I-shaped columns or W-shaped columns that we use in North America and Europe would behave under this type of seismic loading? So at this point, like 7 years ago, what we had so far in the literature, we had some tests conducted on columns. And these tests were mainly conducted on what we call shallow or stocky columns. So these are columns that are less than 40 centimeters in depth. And if I look here at the plastic rotation capacity or the ductility of these columns, we see that there are several of those under moderate axial loads to high axial load develop a very limited plastic rotation in the magnitude of 1%, which can be very critical in the case of a seismic event. We need more than that. So the question was, okay, how would deeper columns, these are deeper than 60 centimeters, would behave under the same type of loads? So we started with conducting experimental research, and we tested about 24 specimens in 2 different labs in Canada, in Montreal. These are the setups that you see here and the specimen highlighted in blue. On the one on the left, we tested cantilever columns, so basically a fixed base and a pin at the location of the inflection point. So these are 2-meter long columns, and they were tested at a 2/3 scale, so around 40 centimeters deep. The one on the right, we were able to test full-scale columns with realistic boundary conditions. So this is a very fancy 6 degrees of freedom setup in École Polytechnique de Montréal. And we are able here to control the boundary conditions at the column top, and we apply as well drifts in all directions. as I will show you in a second. So here are some videos just to break the text that I'm showing you today. So these are the two test programs. Let's look at the one on the left. So this is the one, the 2-meter columns. You can see here it's being subjected to lateral cyclic drifts, and in the same time we are applying varying axial load that goes into compression on one side and tension on the other side, which is typical to what exterior columns would experience under a seismic event. So as you notice here, the main failure mode or damage mode is local buckling taking place at the base, as you would expect. Now the one on the right, here this is with the full scale test. It's a little bit dark, but you can see here that at the top we are able to simulate some flexibility representative of the top joint, and we can apply bidirectional drifts at the top, again representative of true earthquakes, and the column of course is there is axial load applied on the column at the same time. So you can see here local buckling again occurring at the base, and there is some twisting and out of plane instabilities occurring at the later stage. So when it comes to damage progression and failure mode, this is what we found out. Okay, so local buckling is the main damage mode, but this can become excessive after like large rotations, and associated with that there will be some axial shortening. And this axial shortening can be critical if you are considering that this column could be part of a high-rise building, for instance. So this can have some effects on the overall behavior of the structure. In the same time, if you are looking at larger rotations, like more than 2%, you can observe as well that once you get plastic hinge at the base, you can see the column in the weak axis start to kick out a little bit, and you start getting some twisting modes. Now, these two damage modes that you see, we don't design for those explicitly when we do seismic design, so this is something to consider. Using this fancy setup, we were able to quantify the effect of boundary conditions. So before that, most of the tests were conducted on cantilever columns or columns with two fixed end boundary. Now these, what will happen here, you will get simultaneous plastic hinging at the two ends, and you don't observe much out of plane deformation in this case. Now, if you look at the realistic case with a flexible top, what happens is that plastic hinging occur only at the base, and in the same time, the amount of out of plane deformations is about 3 times more, and this is again associated with some twisting. When it comes to the effect of the loading protocol, this is something that has been known before, so we already know that any structural component, its response will depend on the loading protocol or the load history it's being subjected to. So here we were able to quantify that. So on the left, you see the column being tested with your typical, what we call a symmetric cyclic protocol. And this can be conservative compared if you are looking at strong seismic event, because under strong seismic event, what will happen is that the structure will tend to behave asymmetrically. So it will tend to be moving in one direction more, what we call ratcheting. So this is the one on the right. So what you can observe from here, like at the same target rotation, the symmetric protocol actually, the column can develop half the plastic deformation capacity and can shorten 5 times more. So it can be conservative for sure. As I mentioned, one of the important things that we investigated that has not been done before is the effect of bidirectional loading. So on the left, we have, again, these are the unidirectional, so we're just pushing the column in the strong axis. So we have these two protocols, and we developed additional protocols that are consistent with those, but they have a weak axis component. So under bidirectional loading, the difference is not substantial, but if you are looking at rotations, again, more than 2%, then you will start seeing additional P delta effect in the weak direction. So this additional demand causes additional, again, out of plane instabilities and twisting of the column. Now, this gives us very good overview, an idea of how columns behave, but not the total picture. So we want to complement this with some simulations. So we go directly to finite element analysis. So this is the numerical research part. And we had to build a finite element modeling approach from the ground up to make sure it's objectively robust. So we start by conducting measurement of the geometric imperfections in hot rolled sections. And then we recommended some limits that you can use in your finite element model. The same thing we have done with the residual stresses. We did the measurement, and then we recommended some distributions that you can use again in your finite element model. And perhaps most importantly is the cyclic material model parameters. Now, these parameters, in order to obtain them, we have done thorough calibrations with steel coupons subjected to different strain histories. And then by doing optimization for the material parameters, we were able to develop these parameters that you see in this table for different steel grades that are used in Europe, in China, and in the States. So you can directly look up your steel grade from this table, find the parameters, and use them directly in your finite element software. And it goes without saying, we have done thorough validation of the model, pretty much with all the available test data from our tests and from others. And we contributed as well to applying the prediction contest, which we won. So this is all done to make sure that our model is objectively robust and that we can extrapolate it to other cases. Now we have a data pool of almost 150 tests and more than 1,000 simulations. So we can use this to start developing better seismic design recommendations. And we can use them to do some regression and maybe provide some formulas for some important performance indicators. So when I'm talking about seismic design recommendations, this is what we recommended. So in order to limit the amount of strength and stiffness loss under seismic loading, and to limit the amount of axial shortening, and to make sure that we have enough ductility, we recommended these 3 limits. So these are all limits, one related to the local slenderness, so making it more stringent. And then we have another one for the global member slenderness. And finally, a limit for the axial load ratio induced by the gravity load. So when you do those, then you will achieve a minimum performance of the column that is deemed acceptable. I told you about performance indicators. So again, we have lots of data. Easily you can do regression analysis, and this is what we did here. So axial shortening, so now you can predict it with this simple regression formula. You just need to put the axial load, the column slenderness, and if you know the cumulative plastic deformation based on whatever history the column is subjected to, then you can compute the amount of axial shortening directly, which can be very useful if you are assessing damage in the aftermath of an earthquake and you want to see if this column will be repairable or not, for instance. Same thing we have done for the plastic hinge length. So this is another formula that you can use to compute the extent of the plastic zone. And this again can be very helpful if you are doing some kind of what we call distributed plasticity modeling or fiber-based modeling. So here, if you are using finite element, so instead of modeling the entire column with solid or shell elements, no, you do that just in the plastic region where you are going to get the nonlinearity, and the rest of the member is represented with an elastic element. So it saves lots of computation time. Now, this part for the loss assessment framework, we found that, okay, there was no fragility functions that can predict the probability of damage in columns. So we developed those as well. So we started developing defining some damage states relating to the yielding of the column, local buckling, different levels of damage. And then again, in this equation, it's very simple. You just enter the story drift ratio, the axial load, the column slenderness, and then it will give you the probability of being in a given damage state. Again, within the loss assessment, we found that currently, the current methodology to decide if you need to demolish a building in the aftermath of an earthquake, this was based on the amount of what we call the lateral residual drifts. So if you look at a building, you do an analysis, or after an actual earthquake, you look at how much lateral residual drift is there, and then using some fragility function, you can get the probability of demolition. So we updated this with a bivariate one that consider both the lateral drift and the amount of axial shortening. And actually, the amount of axial shortening can be critical, and it can control this decision or this probability if you are looking at high-rise buildings subjected to long-duration earthquakes, for instance. Now, I talked about models for engineering practice in order to do robust or accurate simulations. So in the literature, one of the documents, the important documents, is ASC 41. So these documents provide you with how to model different structure components. So for columns, you represent the column with a single nonlinear spring, and this spring, you assign to it a backbone curve that represents the backbone of the moment rotation behavior under cyclic loading. The problem with this curve is that it doesn't consider the dimensions of the column, the axial load, and different things that affect the behavior substantially. So we wanted to update those. So also, while we are aware of the fact that different loading protocols, the column will behave differently, so we developed two types of backbone curves, one representing the backbone under monotonic loading, the one in black, and another one as the first cycle envelope under symmetric cyclic loading. Now, the moment and rotation parameters using regression, again, analysis and some analytical expressions. Very easily, you go here, you substitute in these formulas, you construct your backbone curve, you put it into your platform for simulation, and you do the simulation directly. So this is for the monotonic curve, and this one for the cyclic envelope. In the same time, these models are used coupled with some what we call deterioration models. And these models, the IMK model, if you are familiar with it, this is one of the models that can do this cyclic deterioration. So we calibrated as well the parameter that's responsible for the amount of cyclic deterioration, which again you can use with simple regression formula. This is a comparison to show you how superior the new model compared to the past version and the current version of ASC 41. So this is the model in black. So you can see here that it does much better job capturing the elastic stiffness, the strength level, the post-yield stiffness, as well as the degradation slope. Now, this model is already published, as you see in the reference here, and it's going to be out in the next iteration of ASC 41, which is supposed to come next year in 2023. Now, moving to the second structure component, which is the column web panel zone. Again, starting by its role in seismic design. So again, when we design frames, the beam should plastify, as you see here on the left. And in most international codes, the column panel zone should remain elastic, or even sometimes very limited inelasticity is allowed. Now, if you actually make the panel zone the weak element and allow much inelasticity, so it will behave like this. So this is the shear force and shear distortion response. And as you see from this behavior, if you are familiar with earthquake engineering, this is something good. They are all round hysteresis. There is no deterioration. So this is something that could be good. The problem is that if you let it go to high levels of inelasticity, like lots of shear distortion, what will happen is that you will increase the strain at the column flange, and eventually fracture can occur in the weld of the beam flange. Now, there has been several guidelines, detailing guidelines to make sure that you reduce this probability of fracture or even eliminate it totally. So this means that this indirectly promotes the use of panel zone in seismic design. So maybe we can make it the weak element. And in order to do that, we need to make sure that we have a good model to represent this behavior. So we collected data from 100 tests, and then we did some comparison with the existing model to see if they are good or not. And here you can see with respect to the elastic stiffness, pole steel stiffness, and plastic strength. So these are all some comparisons that show you that error can be maybe 50% or 2 times more, 2 times less than the measured quantities. So for sure it's unreliable and it needed to be updated. How? Same procedure. You do the same finite element modeling approach that I discussed earlier. You do a parametric study, you complement the experimental data, and then we start looking at different aspect ratios of panel zones, different sizes like thin, thick, and so on. And we started analyzing the stress, shear stress distributions and evolution in the panel zone. And from this, we developed this trilinear curve. Again, this is a hybrid model, so it's mainly developed using analytical expressions with some factors that you can obtain empirically just to make it simple to use. So very easy to use. You can construct the backbone curve, put it again in your model, simulate, done. So how good is it with respect to the existing one? So here you can see some comparison. Again, the new model is in red. Again, even with the elastic stiffness, does a better job capturing the elastic stiffness, and then the evolution of the shear strength, much better, even at large levels of shear distortion. Moving to the third, so we're almost close to the end. So this is a part actually from my PhD, and we were looking at composite beams in rigid connections. Now, how can we model these kind of elements? Well, there is one way you can do finite element model, but as you probably know, this is something that's not easy to do. It requires lots of computation time, lots of experience to do it correctly. The other way is the one in the middle here, that you can use what we call the component method. So you represent each component within the joint, like the steel beam, the shear studs, the reinforcement, the slab, using simple springs, and then you connect those mechanically and you will get your response. But again, this can be laborious a little bit if you are trying to develop this for each connection in your building. The simple one, and the one that's most popular, is the one on the right, where you just have one single spring to capture the entire behavior of the composite connection. Now, we already know how steel beams behave, and we have equations similar to the one that I presented earlier that are able to construct the backbone curve and simulate the cyclic behavior of steel beams. But once you have a composite slab, the behavior becomes asymmetric under hogging and sagging bending, so it becomes asymmetric. So the question was, all right, how much do we need to modify the backbone curve on the left for the steel beam to obtain the composite backbone? So we had 22 tests on composite beam-to-column connections with reduced beam section. We did some calibrations and some statistical analysis. And from this, we provide these modifications simple modifications to strength and rotation that you can apply, and you get your asymmetric behavior. Now, something else important recently that was investigated using finite element simulation is how different would this connection behave the way that we model it, like as a sub-assembly, or this is the typical test that we do in labs. We just use like this cruciform connection, and we test it like that. So how different will this be from the connection in an actual frame where there is continuity? So what we found here is that the connection can actually behave better, and it will experience 25% less flexure strength degradation. And the beam axial shortening, because of the local buckling, it tends to short. So this becomes 4 times lower than the one observed in sub-assemblies. And the reason for that you have the framing action and the restraint by the framing action, the other columns next to the connection, and the continuity of the slab and the reinforcement. Okay, so this is my last component. So this is part of the research I'm currently conducting at University of Southampton. And semi-rigid connections, they are a main part of any structure. They are abundant in construction. You can find them pretty much everywhere in conventional framing and in ductile framing in seismic regions. They come in different shapes and forms. And the question is here that when we design or model these connections, we typically ignore their contributions and we just assume them as pinned or fixed as a simple way of doing things. Now, you can see here that end plate connections, for instance, like extended or flush end plates, like the one shown in the illustration here, can actually develop large stiffness and large amount of flexure strength that it's a shame that we ignore this contribution. Now, the literature, as well as our research recently, suggests that the current numerical models that we have for these connections fail in predicting the response of these connections in a reliable manner. The good news is that there is a huge number of tests that were conducted worldwide since the 1950s, and these, of course, can help us in developing newer models. So this is the task that we have taken, and we're starting developing a comprehensive experimental database for the first time. Right now, we have more than 1,600 specimens, so it's really a huge number of specimens available from more than 200 testing programs. This all dates back to the 1960s, and it's not very easy to find some of these research programs. And this is a multi-attribute database, so we collected information about the testing program, the connection topology, geometry, materials, damage modes, and so on, and everything is tabulated in a systematic manner. And of course, we have the moment rotation behavior for each one of these specimens. And from the moment rotation, we can do some fitting to deduce some parameters like stiffness, strength, ductility, rotations, and so on. And using this data, we can assess the existing models or even develop newer ones. So this is just to give you an example here. So this is for flush end plate connections, which is perhaps the most common one used among the different types of semi-rigid connections. Here you can see distribution of the strength and the ductility of these connections. So you can see here that in the presence of composite slab, these simple connections, bolted connections, they can transfer more than 84% of the beam plastic moment, which is borderline full strength connection. Most importantly, if you look on the right, with respect to ductility, these connections, if detailed properly, they can achieve a very good ductility, and they can have like more than 4% plastic rotation, which is a rough number that we use in seismic design. I said we can assess existing numerical models, and there are a huge number of numerical models available, each one trying to do a better job than the previous one. But perhaps the most important two models are the one we used in design. So we have the one in the US, AISC, and the one in Eurocode, namely the yield line method and the component method. So this is again a sample evaluation using flush end plate connections as example. And this plot shows you the error in predicting, in percentage, in predicting the plastic moment. And you can see that both methods actually does a very good job if you are looking at the median. The median error is pretty much 0, but there is a standard deviation to this error. So actually the error in the prediction can go between plus and minus 50%, which is large enough considering that you are predicting the plastic moment, a very important quantity. And actually, these errors become much larger if you are looking at the stiffness, which is very sensitive to the connection parameters. That's it. This concludes. So now the summary to wrap up. Where we started, I end with where we started. So again, we looked at 4 different structure components in steel moment frame buildings. We looked at frame columns. What we developed, these are all things that you can use right away. We have a validated finite element modeling approach with calibrated material models for different grades. We have new design provisions that you can use to improve the ductility and stability of your columns. We have formulas to predict axial shortening, plastic hinge lengths. We have formulas as well to predict the probability of damage and fragility of columns. And most importantly, we have these numerical models that you can use in simulations. Same thing for the panel zone. We have an open source experimental database that you can access and analyze it further. And we have this updated trilinear shear force deformation model that's usable for high levels of inelasticity. We have an asymmetric model for composite beams, and we also highlighted the difference in behavior between the connection in a true building and the idealized connection in tests. And finally, semi-rigid connections, the very large database that we currently have, and how we are now utilizing it to quantify response characteristics of the connection and develop new prediction models. I promise this is the last slide. Very colorful slide. So anything that we do, we try to make it accessible to everyone and easy to use. So all the tools that I provided today are available packaged in different software that you can use. So for instance, we have FM2D, very easy to use software that you can use to model and analyze buildings with very limited amount of data to enter, and it does everything else. And it incorporates all the state-of-the-art models that I discussed today. We have EARL. This is a software that you can use for building loss assessment to evaluate monetary losses and things like that, and casualties after an earthquake. And finally, we have this Explorer for the semi-rigid connection database, where you can explore all the tests that has been conducted, how they behave, and so on. That's it. Hopefully I'm on time, and I didn't bore you as I promised. So thank you very much, and hope you enjoyed it.
Thank you, Ahmed, for the brilliant presentation. Okay. Yeah, don't worry about it.
All right.
I'm sure the audience found it very insightful. Before we open up the room for questions, let me talk to you about the upcoming SAGED events before I forget. So the next event is co-badged with IFIT and is entitled The Case for Disaster Resilient Housing, Why and How, and it is scheduled for the 10th of November. It will be an in-person event at UCL with parallel live streaming. And then comes the Young SAGED lunchtime seminar on offshore wind turbines, which is scheduled for the 17th of November. So let's open up the room for any questions.
Okay.
Up to you.
No, maybe if I want to. Yeah.
Thank you very much, Dr. Elkady, for this interesting talk. I have mainly two questions.
Okay.
The first one, are these outputs have been adopted, or part of them, by any code, like the length of the plastic hinge,
yes,
the backbone curves, and so on?
Yes.
And the second one, if you can please illustrate a bit more why beams tend to shorten due to the lateral torsional buckling and in the frames.
Okay.
Thank you.
All right. Okay, thank you very much for your question. Let me see if I can go back here. So yes, several of the things that I presented today are incorporated or are being incorporated into design codes. Most importantly, the one with the numerical models for the steel columns. So these are coming into the next iteration of ASC 41, and they are also part of some pre-standard documents by the National Institute of Science and Technology in the US. Also, the seismic design provisions for improved ductility and stability, these are also being incorporated into the Canadian code. What else? The same thing for the column web panel zone, this neutral linear shear force, shear distortion. Again, this is part of these standards for modeling. The equations for axial shortening or plastic hinge length, these are more niche, so you will not find them in your typical design standard. So this will be something if you are doing something more refined analysis, so you would use those. So currently these performance indicators, no, they are not part of design standards because they are a little bit off topic at the moment. But as we go into more advanced models, it will become more common to use these models. The ones for semi-rigid connections, these are, we're still working on those, so it's still a long time until we have better models, and we try to convince people to adopt them in codes. I think your second question relating to axial shortening of the beam. So yeah, so the beam or beam column, you are getting local buckling, and once you get this local instability, the length of the beam need to go somewhere. So once it buckles, it needs to shorten, right? Similar to the beam column. But in an actual frame, because you have this restraint by the different beams and the other columns connected to your beam end, so these try to pull or undo the buckling, all right? So then this will translate into tensile axial load in the beam. So the beam is trying to shorten because you have local buckling, and in the same time there is tensile forces like Ketten reaction of a sort trying to pull it back together. I hope that answers your question.
So it's due to the local buckling and the lateral torsional buckling?
No, not lateral torsional buckling, just local buckling. Thank you.
Thank you very much for a very nice presentation. I have a couple of questions. The first one is when you refer to the vertical shortening,
Yes.
right? And you said that at some point it governs the fragility, right?
Mm-hmm.
Is that because presumably that and the residual are collinear in some way, right?
Yes.
So is that because it stops being collinear?
Yes, thank you. This is a very good question, actually. So if you check the reference that I have in this slide, it has more information that I didn't show here, just to keep it simple again. But yes, so depending on the type of seismic event, they would be collinear in some cases, but in some other cases, they are not correlated. So you would get an earthquake that produces a very large lateral residual drift, but no axial shortening, or limited axial shortening, and another one that you will get large axial shortening, but small lateral residual drift. So one example that I mentioned is like if you're looking at high-rise buildings subjected to long duration seismic event, a strong seismic event. So what will happen is that you will tend to get lots of local buckling, but at the end, the amount of lateral deformations, because the structure is not pushed in one direction strongly, so it keeps moving around its origin, and you're still developing local buckling. So you get axial shortening, large enough meaning, but the lateral residual is limited. So they are not collinear. So that's why you need this kind of bifragility.
Okay, thank you.
Yeah.
And the other one is in your final slide, or one of your final slides, you show that the yield line model
Yes.
sort of outperforms a bit the component-based model in the estimation of variation, right?
Yes.
What do you think is driving that?
Well, okay, in this plot, okay, I tried to make it very simple. As you see here, this is like you have almost 120 specimens, and actually the database for flush end plate connections, it has 600 specimens. So in this plot, I'm trying to be biased towards these models, and I'm only selecting the connections that are within their limit of applicability. So for the yield line method, it considers the end plate and the column flange as for the yielding mechanism. It doesn't consider, for instance, the panel zone behavior or the beam that can buckle or the bolt that can elongate compared to the component method. The component method is, of course, much more generally applicable. So again, there are underlying assumptions in both of these methods that tend to
So
trigger.
you're making sure that the specimens there obey
Exactly.
failure.
Yeah. So I'm biased here in these plots, but if I'm plot everything, the errors, it will be everywhere.
I see.
Yes. But thank you. That's a good question.
Can I follow up on the first question?
Okay.
I was actually having a confusion whether these two are the same thing, like the axial shortening and the lateral displacement. Wouldn't they be guided by the same thing? Or on the other hand, is it the same direction of buckling or the same mechanism that is governing these two? Like you could have a local buckling in one direction that governs the axial shortening and another mechanism in another direction that governs the lateral drift, depending upon the direction of your loading. How does that interact? Like, is that one and the same or could be different?
Okay.
And one second question
Yes.
is, if you know, I mean, if we can predict the location of that local buckling, couldn't we do something to avoid that? Like as a, strengthening or having some extra strengtheners there?
Yes.
Okay, thank you.
Okay, thank you. I'm getting very good questions today, so I'm happy for that. So for your first question, let's talk first about the lateral residual drift, okay? So this metric is very sensitive. Like even models that are trying to predict this amount, given the seismic intensity or the building shape or anything like that, it highlights that this parameter is very sensitive, because what will happen is you could get an earthquake, the building goes right and left and so on. You get lots of plastic hinges everywhere in the beams, in the columns, in the panel zone. And then the building, by pure chance, it moves close to the origin at the end. And in that case, if you look at the residual drift, well, the building is in its original position, but this doesn't mean that damage had not happened in the structure components. So this metric, the residual stress, can be, the lateral residual drift can be very sensitive in that case. So it's not always a good metric to say, this building has been damaged or not. In general, yes. If you see a large residual drift, for sure there is damage. But if you don't see it, this does not mean that there is no damage. Which brings me back to this, there is no collinearity in different cases. You see lots of axial shortening or local buckling in the beam, plastification everywhere, but the value of the residual drift is small. Okay, so this depends on the event itself. Your second question, I forgot.
The local buckling can be a
Yes. Yeah, so with respect to the local buckling in columns, so you would say, okay, let's put more stiffeners, but even if you put more stiffeners, well, local buckling will occur in the weakest part. So it will occur a little bit higher, and you will still get it. So how you can avoid this? Well, you can minimize it. You can minimize it how? By these design provisions to make sure that local buckling will be very limited, even if it happens. And there are even now more research that you can do what we call like damage-free connections or at the column base and so on. but these are more niche applications that you will see like in countries with very strong seismic experience, like New Zealand or something like that. But for your typical convention design, you would use these recommendations. They are simple enough to employ in the code, and that's it. All right? Yeah, that's pretty much it. Thank you. Right.
Thank you very much for this interesting presentation. I'm familiar with quite a lot of details because I've been following it for a number of years.
Yes.
But I just want to use your insight, having worked on this for several years and in great detail, just to give an idea, if you are designing a structure like the one you were showing, and you have a choice between using a bare steel frame or a composite frame, you know, which one would you personally choose and why? I mean, you've shown a number of considerations.
Yes.
And obviously there is a tax to pay in terms of the design, the complexity, and so on.
Yes.
So what are your views on, I mean, I guess there are no clear answer, but what are your views on this? And the same also in terms of rigid connections and semi-rigid connections.
Okay.
Thank you very much.
Right, thank you very much for the question. These kind of questions that are a bit overview, so a bit challenging to answer. So it depends. Yeah, I mean, if we are looking at the design like in North America, when we are designing this kind of moment frames, we don't really consider the composite action. So for instance, when you are trying to make sure that the column is stronger than the beam, you don't consider the increased strength of the beam due to the composite action, although it's made like that in practice. So in what we actually proposed back then is to include the composite action as part of your design. So you compute the strength of the beam and you design the column to be stronger than the composite beam. But of course, if you have the two options, I would say, yeah, utilizing the composite action is a good thing as well because you are benefiting your structure. But of course, your design needs to consider it. The problem is that we don't consider the composite action. So then when you have the composite effect on structures that are designed as bare steel frames, then you can start getting some local collapse mechanisms that you didn't anticipate because of this issue. So in short, yeah, I would design as a composite. So I would go with the composite construction, but the design need to consider this as well. So the construction is, the design is guided by the construction itself. And the same thing applies to semi-rigid connections or full strength connections. Again, you can amplify the strength of the connection by 50% or even 100% more by just adding some studs and working in a composite way. And there are even different details, as probably you are familiar with, detailing that you can minimize the amount of damage in the concrete or in the rebar, and then you can localize damage away from the column and so on to improve repairability after a given hazard. Hope that answered the question in a political way. Thank you.
Any other questions? Surprisingly, there are none from the online audience.
Okay. It's typically the other way around. But okay.
No, we are talking about bare frames, no, without infill masonry or other material.
Yes. So
Any insights into what happens if you have that?
yeah. Well, insights.
Thank you.
Okay. Thank you. From myself, no. I mean, there are better researchers with more experience about the effect of infill masonry or these kind of infills on the response of moment-resisting frames. But again, one step at a time, I think. So first, you try to fix the issue with your main structure, and then you can move to other contributions, like as we mentioned, like going with the composite action, and looking at the semi-rigid connections, contributions, and then moving to additional contributions by infills or non-structural elements that can actually affect the response. But there is good literature on this as well.
Okay, then since there are no more questions for Ahmed tonight, I will thank again our speaker for the great presentation. The IC bar unfortunately is closed, but we will continue with drinks at a nearby pub just 100 meters away. You are all welcome to join us. Thanks again, Ahmed.
Thank you very much. Thank you.